Okay, this is problem 23 from chapter 7. We have this tabletop with a spring attached to it and this mass here, this box of 2.5 kilograms. It says we push this box into this spring so that it stores 11.5 joules of energy into the spring, and then we release it. And it's wondering, well, part A is what is the max speed that this is going to reach when it's released, and when does that occur? That's for part A. So we know we're given that the max potential energy that we've created when we've pushed the spring down with this mass is 11.5. So to get the max speed, we can just use the equation 1/2 mv squared, solve for v, and plug in this potential energy in for k, because the maximum kinetic energy is just going to be whatever the maximum potential energy that we achieved. I hope that makes sense. But we'll plug in for that and we'll solve for v, which is going to give us first off, when we solve for v, we get v equals the square root of 2 times k over m. And then we just plug in. So we're going to get the square root of 2 times 11.5, which is our maximum kinetic energy we can achieve, divided by our mass, which was 2.5. That gives us 3.03 meters per second. So that should be, this should be the maximum speed we're going to achieve. And that should happen when our potential energy is 0, because we used this 11.5 considering that once we've used all the potential energy, it's all been converted to kinetic. So when potential energy is 0, that's when we should reach our maximum speed. That's part A. So part B, let me read it. It says, what is the greatest acceleration of the mass, and when does that occur? So we're going to be using the equation F equals kx right? Oh, but first we need to use the equation 1/2 kx squared and solve for x. Sorry, let me just solve for this again. 2 times. Yeah, let me just show you what I'm doing here. So we have 1/2 kx squared. We're going to solve for x. And this is going to give us the distance that we're going to need to, the distance we're going to need to use in order to find our acceleration. So k, we're given that our force is 25 newtons per centimeter. We need to convert that to newtons per meter. And so we're just going to times it by 1,000. Yep. So we're going to have let me explain this a little bit better. So this is a U, by the way, not a 4. So 2 times our potential energy over K. And so it's going to be 2 times 11.5 all over 2,500 because we converted from centimeters to meters. And that comes out to 0.0959 meters. Right here. So we're going to need that for this next part to figure out the acceleration. So we have F equals kx here. We're going to just plug in to find the force here, the max. Our force equals 2,500 times what we just figured out, that distance, 0.0959. Running out of space, but it gives us 240 newtons. So now we have our force, 240 newtons. Finally, we can use F equals ma and solve for a to figure out the acceleration. So if we do that, when I get closer here, we used F equals ma, we solved for a, so we get our 240 divided by our mass, 2.5, it gives us 95.9 meters per second squared. And that is the greatest acceleration of the mass. And that occurs as soon as the mass is released, because anytime after that, it's going to be starting to slow down. So as soon as the mass is released from the spring, that's when this acceleration occurs.